Hello everyone, today we'll be presenting about our project.
Our project is titled Simulation Framework for Embedded Processor and Peripherals, and we focus on developing a browser-based open-source simulator designed for learning and experimenting with embedded systems. Understanding low-level computer architecture is essential in embedded systems education. However, most existing simulators are either outdated, closed source, or lack important features such as peripheral simulation or visualization tools. For example, JsSpim is great for 8051 microcontrollers, but it's not open or extensible. So our goal is to create a modern, student-friendly, and modular simulation framework that's accessible online and allows users to explore how processors interact with peripherals. Our project has several main goals. First, we want to make it as open source as possible. We want a simulator that's readily available online for easy access, with a modular framework to make room for expansion or improvements. Next, it also has to be accessible, such as supporting browser-based execution and be able to run MIPS32 as the base architecture since it's widely used in academia. Lastly, it also has to have many features such as peripherals, a code editor, memory-mapped I/O, timer interrupts, and system calls, to name a few. The simulator is divided into three main layers: the web front-end, the simulation core, and the peripheral modules. The front-end provides the user interface, where students can write and assemble MIPS code directly in the browser. The simulation core, built on JsSpim, executes the MIPS instructions and handles memory and I/O operations. Finally, the peripheral modules such as the LED, UART, and 7-segment display are connected through memory-mapped I/O, simulating real embedded system behavior. Each of these modules will update dynamically through the memory-mapped I/O system, showing how the processor interacts with hardware in real time. This modular design ensures that feature components like LCDs or keypads can be added easily.
So now I'm going to give you a brief demonstration of our finished simulator. So over here you have your register views and your data segment views, and in the middle will be our text editor, as well as your output, log, and user stack display over here. As for the peripherals, you have your 7-segment display and LED display, and also an additional UART interface. So to start, you can choose from our given MIPS assembly files, which are provided here, or you can even upload your own file from your local computer. So let's say that we choose this file for our brief demonstration. If you've made any changes in the file, you can assemble it to get it running, or you can even save the file to your local computer. So let's say that we want to start the code. We can press play and it's going to show the output hello world over here. And to get it running again from the beginning, you can press the reset button and it's going to start executing again from the start, like so. And if you want to show the execution step by step, you also have the step button over here, which you can press. And you can also adjust the execution speed to your liking, as well as add some breakpoints by pressing on the individual addresses, like so. As for the text editor itself, let's say that we make some changes to this code. So for example, we change hello world to something else. You need to assemble it first to get it running, and pressing play will give you a different output. As for the timer interrupt, we have our timer interrupt code over here, and if we assemble it and play to get it running, you can see that the timer interrupt works because we got a timer interrupt, which is displayed in the output over here. And for the peripherals, which include our 7-segment display and LED display, you can see that if we run this code, the 7-segment display is going to start lighting up according to the instructions. Same thing with the LED display, it's going to start lighting up as well according to our code and our instructions. As for the UART interface, so if we type a message over here in the transmitter and send it, you can see that the receiver will receive the message and is going to display over here.
For future development, we plan to enhance the simulator with more peripherals such as LCD display, keypad input, or an ADC simulation, add cycle-accurate simulation to analyze timing and performance, memory and register visualization for better learning experience, and a plugin system allowing developers to integrate custom peripherals easily. These improvements will make the simulator not only a classroom tool, but also a platform for embedded system research and experimentation.
That's all from our presentation. Thank you for listening.